Okay, welcome back. This is the final video on the dot product and covers material in section 10.5. And again, there is a ride-along PDF in color of these slides. I've updated it recently, and that will help you as there's 4 slides to a page. It's in color, so if you print it out, you can take notes on it, have something to reference. And this way, I'm hoping that what we can do is concentrate on the ideas, and you can write along and take notes if you wish. Okay, here we go. One of the ideas is if you have a vector, you can decompose it or break it down into 2 orthogonal vectors, or vectors that meet at right angles, whose sum is the original vector. So in the example we're looking at, the inclined plane, and when we saw this in vector operations 1, we have vector f is composed of the vector sum of f1 and f2. And don't forget, what we could have done is we could have put vector f2 here, and then you can see it's the old tail to head to head, and that would be vector f. Okay. Same thing happens here. In each case, vector v is the resultant of the 2 orthogonal vectors v1 and v2. And that's what we're going to work on now. We're going to work on breaking down a vector into 2 orthogonal vectors. Okay, this is the theory. Here we go. Okay, let v and w be 2 non-zero vectors which sum the same initial point p. Vector v can be expressed as the sum of the 2 orthogonal vectors v1 and v2. And you can see here, this is just the same thing, right? Because if we solve for v, it's v1 plus v2, but we're writing it in this form because we want to be able to get v2 here, whereas this part of the expression gives us v1. That's the idea, okay? And we're going to stick with a certain standard here, and the standard is that v1 is going to be parallel to our given vector w. It could be a multiple in length. In fact, it would be a scalar multiple in length. It could be going in the other direction, but the idea is it's going to lie on the same line, the same incline, the same angle as vector w. And v2 is going to be orthogonal to it. So that's going to be our pair. Now, we've already learned earlier that the projection of vector v onto vector w is given by this expression. So let's just go back real quick and show you where we did this. Okay, and this was what we did last time. What we did is we were working on the projection of vector v on vector w, and we found that this was the length, right? We used the idea that the cosine theta was the length of the projection over the magnitude of the length of vector v, and then this was a scalar quantity. So to make it into a vector in the direction of w, we multiplied it by the unit vector in the direction of w. Okay, so this makes it a vector without changing its size. Okay, now the next idea is we wanted to get this in a form of a dot product, because a dot product is very useful. So if you go back and you think about the formula for v dot w, what we're missing here is a magnitude of w. So what we're going to do, we're going to multiply top and bottom by the magnitude of w, which of course is 1. Okay, so we're not going to change the direction, we're not going to change the length. All we're going to do is we're going to put it in a form where the dot product appears. It's going to make it a little more useful. Okay, so we got the magnitude of v from here, the magnitude of w times cosine theta, that's the dot product. And then on the bottom, we're going to have the magnitude of w squared, and we're also going to have vector w. Okay, so this is a scalar, and this is w, so the projection of v onto w is going to be a scalar multiple of w, which means it's going to lie in the same line as w, but it's going to be longer or shorter or reversed in direction. Okay, all right, so now let's move forward again to where we were. Okay, So here's the idea, and this is what we're going to be doing. So this is the formula that we had derived earlier. We just talked about it, and this is going to give us our V1, and here's how we get V2. So let's immediately look at two examples. Example number one says find the vector projection of vector V, which is I plus 3j. It could be angle bracket 1 comma 3, right? But we're going to try and use I and j onto the vector I plus j. And we're going to decompose V, means we'll break it down into its component parts, to two non-zero vectors V1 and V2, where V1 is going to be parallel, in other words, same direction as W, and V2 is going to be orthogonal. So first we're going to do the the algebraic part of the math, and then we're going to look at some pictures and see what we really did. Okay, so what we typically do, step one, we begin with the appropriate formula. Okay, so this would be the projection of V onto W, which as you saw, we symbolized by V1. Okay, whoops, where did we go? We got lost. There we are. Okay, so now we just work this out. V dot W is 1 times 1 is 1. 3 times 1 is 3. 1 and 3 is a 4. So the top is going to be a 4. And the bottom is the magnitude of W squared. So we work this out. 1 squared plus 1 squared is 2, radical 2. Radical 2 squared is 2. So we get 4 over 2 is 2. So we get that V1 is twice W. In other words, it's 2I plus 2J. Now to get V2, we have to understand that V1 plus V2, those are the two vectors that added together make V. Therefore, V2 is V minus V1. So here's V, right? This is the vector given, and V1 is what we just worked out here. So we subtract them component wise. So 1I minus 2I is negative 1I, and 3I minus 2I is 3j minus 2j is 1j. So these are the two vectors, V1 and V2, whose sum would be vector V, and they are orthogonal. So now let's take a look at what's really happening visually. Okay, so here we go. These are the two vectors we started with. Vector V is I plus 3j, right? We started here. It's a position vector. We went over 1I and up 3 to 3j. So this vector in fancy blue is vector V. Vector W is I plus j, which is right here. So this is what we started with in our problem. And we computed V1, which is on where it's along the same line as vector W. Okay, maybe it would have been down here, but that's okay. It's on the same line that vector W lies, and we computed it was 2I plus 2j. So here would be V1. It's 2I plus 2j. Whoops, what happened? We got lost. Okay, so this is V1, and V2 is the perpendicular. Okay, so look at this. You got V, and we got V1. We do a subtraction to get V2, and what we got was minus I plus j. So if you start from the end point here of V1, minus I up and go 1 unit left and 1 unit up. So here is our V2. These vectors are orthogonal, okay, and together they add up to vector V. All right, so I think looking at the picture is probably helpful. It's helpful for me. Keeps me a little straight on what's going on. Let's do a second example. And maybe you want to pause this video and write this down just to see if you can work it out for yourself. So we'll take a pause. Okay, and if you're back, I hope you had some success. And what we're doing, again, we're decomposing a vector into two orthogonal vectors. So given vectors V, 2I minus 5j, and W, I minus j, decompose V. And we're using the same strategy again. The two vectors, V1 and V2, where V1 is parallel to this other vector W, and V2 is orthogonal to W. So for V1, we use our basic formula. So step 1, write the formula down. Step 2, substitute in. Okay, so V dot W is 2 times 1 is 2. Negative 5 times negative 1 is 5. 2 and 5 is 7. So we have a 7 on top. And the magnitude of the length of vector W is 1 squared, and negative 1 squared is 2, radical 2, and it gets squared, right? So we get a 7 here, we get a 2 here. So V1 is 3.5 times W, or it's 7/2 W. And you multiply it out. Here's your W. And this is a scalar multiplying vectors, so it's 7/2 I minus 7/2 j, and that would be vector V1. And in V2 is the original vector V minus the vector we just found. So if you made a mistake here, this is going to lead to a mistake here. So you got to be careful, step by step. So here's V, right? 2I minus 5j, and V1, where we get V1 is right here. So this is 2 minus 3.5 is negative 1.5, so that's negative 3/2 I. And negative 5 minus a minus is a plus. So negative 5 plus 3.5, right, is negative 3/2 j. So here is our vector V1, here's our vector V2, and again, let's take a look at a picture, diagram. Okay, so vector V is in the heavy blue vector. It's 2I minus 5j. So here's vector V, and vector W is I minus j. So here's vector W, and we computed that V1 was 3.5 times the length of W. It was 7/2 W. So, right, this would be 7/2 I and minus 7/2 j. And so this is the projection. We're shining a flashlight from here onto the line of W, and this is our shadow. V1 is our shadow. And V2 is perpendicular to W, okay? And as you can see, it's going to, V1 plus V2 will sum to W, and we did it as a subtraction though, right? We did V minus V1 to get V2. Here's what we got. And if you take a look at this, starting here, we're going back 1.5, down 1.5. That's exactly what that says. Minus 1.5 in the I direction, minus 1.5 in the J. And so these are our component vectors. Okay, so it's not easy. I mean, so you practice a few. There are some examples in the book. They don't always come out that nicely. I tried to pick some. The first example worked out to integer values. This one, this one has fractional values. That's going to happen. Also something that you should look out for. And we saw this earlier. I just want to bring it to your attention. Where is it? Right over here. If the angle is obtuse, then the projection, which is our V1, is still on the line of W, but it's in the opposite direction, okay? So it doesn't have to have any overlap with W. It's in the line of W. So this would be our V1 if theta were obtuse, and right here would be our V2. And, you do the computation, you make a diagram, and hopefully you should understand what's going on, okay? So be well, and hope to see you soon. And I will be posting up a problem set take home on vectors probably in the next day or so. Okay? Be well.